Okay, testing, testing. So having basically a soldered exhaust fan here. I don't know if it's too loud or if anybody can hear me. Or if it's too dark. Okay. Looks like the audio is kind of filtering out this fan noise. So maybe I'll just wait around, see if more people can join. But in the meantime, I just thought I just test the prototype. I just kind of thought of this, like, I don't know why I didn't do this earlier, but it's better to like test this live, I think, rather than like, I think sometimes the video can be heavily edited and like people might not, I don't know, these Kickstarter videos these days are a little bit too good to be true. So I can understand some skepticism. So I'd like to go and try, let's see, maybe can't, it's hard to see the monitor. It might be blowing out the, might be a little too bright. Let's see. And this camera's not the best quality. I don't have a real good live streaming setup. So I'm gonna try and adjust this light, see if I can make it a little less. You know what? Let me get a piece of tape and just make that light a little bit softer. Okay. That's a little bit better. Anyways, this is 12 gauge wire, and I didn't. So it's a little long story, but anyways, during this project, I found out that car audio installers, they like really quick soldering, so like 5 seconds heat up time, and they're using soldering irons that are very similar to Solderdoodle Plus, but they're very expensive, and they have a momentary switch. And I was like, oh man, because what I was, it's basically full blast on, but when you're a professional car installer, you just hit it for 5 seconds and then let it go. And so there's no real temperature control. They just hit it, full blast, turn it off. And actually, if you hold it down too long, it will destroy the heating element. And this doesn't have temperature control. It's all duty cycle control. What that means is if you have temperature control, you need a very large thermal mass. And nearly all the energy in a temperature control system is used to heat up that thermal mass. And that's what gives you that constant temperature. This is a very low thermal mass, so it's very difficult to control by temperature, but what you can do is you can pulse it on and off at a duty cycle, and that's what we're doing here. We're doing, like, if I turn it on, that first light is 0, there's no duty cycle. You go to like the second level, and then or the third level, and then it basically goes from like 5 seconds off, 1 second on, to like, 3 seconds on, 1 second off kind of thing, and it just keeps going up and up. 3 seconds off, 1 second on, and it keeps going up and up until the maximum power is 5 seconds on and 1 second off, which is kind of like 83% duty cycle. And this was designed in order to prevent the tip from destroying itself. But then after talking to these car audio installer guys, they don't mind having that as a risk as long as they can get a 5-second heat up time. And so because this is all controlled through a microcontroller, we can adjust these settings in the final production. But what I thought to myself is, like, instead of just, so we tried 100% duty cycle, like full on, no off time, and it did that kind of, this tip would actually glow red hot. All right, so what I was thinking is, okay, well, I want to make this for people who want to do crafts, arts and crafts, and all ages, and so I wanted to do it, kind of like reduce the power output on purpose in order to like make it more safe. And I didn't even think about this application for car audio installers. So what the idea is, and actually when I got this prototype made, this last high maximum power was actually a little bit more powerful than when I was originally testing the development board. So actually I can show you all the spaghetti. I mean, this is the original Solderdoodle Plus right here. This giant spaghetti monster, right? So it went from this, and we designed the control system based off of this, right? And here's the batteries dangling and development boards dangling everywhere, right? And then when we got the prototype, I have a feeling that all the just increase in efficiency, just kind of making the boards, from, I can show you the bare boards. Well, different one. To this, right? So that, so here's the first prototype, right? This giant mess, and then it turned into this, right? And so, like, I have a feeling it gained a little bit of efficiency, not like losing a tiny bit or increased little impedance in the spaghetti monster. And then when we went to the prototype board, the same 5 seconds on and 1 second off seemed a little bit more powerful than originally anticipated. And so if you left it down, if you left that power button down for too long, this tip will glow red hot. And then so in the Kickstarter video, I actually did all my tests. When I found that out, I dropped the power down a little bit to like either 1 or 2 steps below. And that's how I got that 14 gauge wire thickness limit. Now, what I like to do is under promise and over deliver. So I have a 12 gauge wire that I soldered, but I didn't show this in my Kickstarter video because I was like, oh, maybe maybe I'm going to actually, for safety reasons, reduce the power level for the final production of it. So instead, you know, I just did the Kickstarter video with the 14 gauge wire. So what I like to do is just do a live test with maximum power and do soldering with the 12 gauge wire. And all the safety features that I was thinking about for the car audio installers is what I can do is for this maximum power level, which has the possibility of making this tip like overheat, turn it into like something like a pro mode, where this maximum power level kind of like behaves a lot differently, very differently from the other power levels, where the max power level will actually like go 100% full blast for like maybe 10, 15 seconds, and then like do automatic shut off, like cool down, like so you're basically preventing any overheating, but you're getting like a blast of like hot energy into your working area. And going back to these tips with low thermal mass, so almost all the energy gets directed to the tip because there's no thermal mass to really heat up, and that's why you can have a basically a similar performance with a 10 watt. This is actually 10 watts. Very similar to performance. 10 watts, like just full blast with a low thermal mass, is equivalent to like a 60 watt like soldering iron that plugs into the wall socket with a large thermal mass. So those are like, I have a feeling they're almost like, I want to say probably like maybe 20% efficient, you know, like very low efficiency, but you get that stable, like constant on temperature control, but it comes at a cost. And this one is just, the heating element is built into this tip right here, and then it just goes right to the tip. But then you have to deal with these kinds of control schemes that I'm talking about, which we can do because there's a microcontroller in here. So I'm just going to go ahead and cut a piece of wire, this 12 gauge wire. And just strip it, and then go ahead and solder it. And after watching some car audio videos, I learned that the way that car audio installer videos, they get the two halves and they just kind of like mash them together like this, and then they do a little twist like this. Okay. So then I'm gonna stick it in here. Let's see if I can solder in a way for you guys to see. Oh, okay, I'm done. Try that again. Maybe I'll do a little tighter. Let's see if I can move this a little bit closer. Okay. And by the way, this is lead-free solder, so it's a lot more difficult to solder than leaded solder, which is why I did that Kickstarter video with lead-free solders, because just to show it was able to do that. I'm just going to put some flux on here. All right. Let's see if the angle is right and you can see it. Okay. Nope. It went into sleep mode because it was like, it has that actual, like, if it's not being used for like 5 minutes, it turns off, so you just hit it 3 times. Turns back on. It's a safety feature. Okay. So here we go. Oh yeah, full blast. See that? Maximum power. And then there we go. Now push it, and now it's on. Smoking. Okay, it's melting the solder. Now this is a big thermal mass, so it's going to take up a little while to actually heat up the wire. So I think it's kind of heating up all the way through. I'm just going to put a little bit more flux on there. Some of it actually kind of dripped off. So you want it to kind of wick into there. And that's how you know it's like a good solder, if you can kind of see basically the kind of fibers of the wire poking through the solder. Well, not bare metal, but like just the shape of the individual like wires. That means it's kind of wicking in there like a into the center of that bundle. So the original Solderdoodle could not do this because it was just too underpowered with that single cell battery. This is two cells in it, and try to make it as efficient as possible using the best power regulators I could find. They're not cheap either, but so I'm going to look underneath, make sure the solder is getting underneath as well. There's a big drop of flux there. We go from the bottom back to the top. And this whole like assembly from these clips all the way down through the wire is completely hot. Like it'll hurt if you touch it. Like that's how much heat's coming out of this thing. So I mean, at this point, this is like basically like a corded device that you would, you know, like a typical like 60-watt soldering iron might be able to do, and sometimes even they have a little bit of trouble. Now you do need flux to do this, but you know, the original Solderdoodle could not do this. All right. And the case here, I mean, this is a prototype nylon case. It's not like melting, which is great. But that also like just me being able to like touch this part of the case kind of shows you that most of the heat's coming out the tip. So I'm going to wait for this to cool down. It's pretty toasty. Yeah, I'm just going to wait for it to cool down a little bit. And maybe, so again, this is 12 gauge wire. The most I could do with the original Solderdoodle, I don't know if you want me to like try this, the original Solderdoodle, but this is the original Solderdoodle, right? The maximum this guy could do was like 24, 26 gauge wire, and even then he kind of struggled because you had to make sure it was fully charged. About after a half hour, the battery voltage of this goes down a little bit. Now, I'm not trying to, talk down to the Solderdoodle, but it's just the fact that it's got, it's not able to do as effective power control because it's a single cell. So single cell, maximum charge, it's 4.2 volts. And at the minimum, its minimum voltage is 2.5. So in between, the voltage is fluctuating. And so the power of this fluctuates with it. So the difference with Solderdoodle Plus is you have two cells. Here's the circuit board. So two cells in series. And they're actually on isolated ground, so that means that each cell has its own charge controller, and which means that you don't need it's basically cell balancing in real time. So they're never over voltage or under voltage, but in series, you have a voltage between 5 and 8.4 volts. And with that, you can regulate down to 5 volts very effectively. And so you get a constant 5 volts out with the two cells because you have a high voltage regulating down to a low voltage. And that high voltage is always maintained above at least 1.1 volts, I think, is what we came out with, above the regulated voltage of 5 volts. So it's constant 5 volts, 2 amps, like no matter what. So that's what the Solderdoodle Plus has over the original Solderdoodle. So actually, why don't I do that test and just like compare it to the original Solderdoodle? So I'm gonna take this off. And the tip should only take like a few minutes to cool down because it's such a low thermal mass, it just gets cold really quick. Yeah, so now I could just touch it with my hand. Okay. I think I fully charged this. Yeah. Yeah, it's not. Charge controllers. This is fully charged. Okay. So let me do another. Actually, I'll see if I can get a good zoom in on this. But it's fully soldered. That brown stuff is the kind of a burnt toasted flux. I can clean that off actually. A little bit of Q-tip. see. Whoop. So I'm just gonna clean that off. Probably need more of a scrubbing, like maybe a paper towel, but I don't know. Kind of get the idea. Now this is lead free, so it's not going to be as shiny as leaded. Leaded is very, very shiny. Lead free, when it you can get it shiny, it's just not as consistent. So it tends to after it flows and hardens and cools, it gets more dull, but that's normal. Anyways, it's a little bit less. I try to take off as much the flux as I could, but if I got in there with a little more elbow grease, I could take the rest of it off. I don't know if that's too bright or if it's. Let's see. I don't know. Let's see. Or if it'll even focus. I don't even know if it's focusing. Anyways. Yeah, it might be a little blurry. Might even be too bright. Okay. Yeah, and my back is to a window. That doesn't help all that much either. But it's solid. It's not. That's something. So I'm going to go and we'll do another one with the original Solderdoodle. Maybe I'll just keep doing this until I run out of wire. Oops. Or unless someone has any ideas if they want what they want me to solder next or something. That's doable as well. Oh, got my finger in there. One more time. All right, so this is just, I'm going to try the original Solderdoodle, which is fully charged. Doing the same thing I did last time, put a little flux, lead-free solder. Here we go. So first, you gotta wait for the tip to get hot. And see how long it takes before it can melt the lead-free solder. And you can already see it's taking much longer, just a few seconds long. Okay, now it's melting the lead-free solder. And it is definitely having a hard time penetrating the thickness of that wire. So I can get a glob on the tip. It's allowing me to melt onto the tip of the Solderdoodle, fully charged Solderdoodle. So it's probably outputting at this point 4 volts, probably like 1.8 amps. So it's not quite 10 watts. So what this means is I'm getting like a surface surface soldering. It's not like wicking. It's not. You know, I'll even put, like I did last time, a little bit more flux. See if that helps. See, it's not even getting all the way in there. It just kind of melts on the tip of this Solderdoodle tip, and then this is the same tip that I used on the Solderdoodle Plus. So it's the same chisel tip. Nothing has changed other than I'm just using the original Solderdoodle. And I think this was the little bit of a, I mean, it works fine when you're doing 24, 26 gauge wire. I mean, little Arduino projects, you're soldering to like a breadboard like this, you know, it's fine because your wires, you know, they're not going to be this thick. They're going to be little thin wires and stuff. So, but if you, it's not like a replacement, total replacement for doing everything, right? So, I mean, I think that's a good enough test. And even if I hold these, I can feel just holding these alligator clips that they're not as hot. They're just like, they're not cool to the touch. They're a little warm, but they're not like, ouch, you know, kind of hot. So that's all I could do with the original Solderdoodle. I mean, it's just surface. It's not even wicking all the way through. Put the same amount of flux, maximum power, fully charged, and that's the original Solderdoodle. So I'm just going to put this back on. Make sure this is not super hot. Swap out the tip. Put on the Solderdoodle Plus. Is this off? Oh, I turned it off. All right. Now I'm just going to do the same thing. You know, I'm not even going to put more flux. I'm just going to assume there's nothing. So go to full power, and then just start heating it up, see what happens. It's already ready to go. So hopefully it can melt what's on there, and then also just like start wicking into the wire bundle. Like I said, it does take a little bit of time for the whole like bundle of wire to heat up. I don't know, maybe 10 seconds. And then once that temperature of the whole bundle gets to a certain point, then it starts wicking in. And I can already see it's starting to wick in. So it's not just a surface solder, it's actually going all the way through. Now I'm also going to go underneath it because some of the flux is like dripping below. Okay. Go back to the top. And like I said, you want to kind of see the not exposed wire, but like the shape of that bundle of wire. You don't want to see like a giant like round glob. You want to see kind of like a little bit of the, you know, what do you call it? Fibers kind of plated fibers of the wire plated with the solder, basically. And this is 10 watts. This is 5 volts, constant 2 amps. And it's just, the duty cycle on this is just 5 seconds on, 1 second off. And we can actually, like I said earlier, the idea, especially for car audio installers, is make this maximum power setting, that last LED right here, like instead of like 5 seconds off, 1 second on, like turn it into a pro setting. So if you want, like, you know, these are just regular, these levels down here would be like regular duty cycle controls, you know, 50%, 25%, 75%. And then maybe the last maximum power could be like a pro mode, which is just like for situations like this. You just want to heat up as fast as you can, maybe less than 10 seconds, ideally maybe 5, 100% full blast, and then you can feather it either manually, just kind of like feathering it on and off like this, or it has like an automatically like safety shutdown. If you hold it down for longer than like a minute, it just shuts itself down. In that pro mode, it'll just like reduce the time it needs to like melt solder into large like speaker wire, for example. All right, so let me. So I guess what I'm saying is, Solderdoodle Plus, this is a prototype controller with prototype control scheme. We can adjust that to make it even more powerful and have a little bit more fancy safety features built into it. But these pro car audio installers don't necessarily need all that safety, because some of their equipment is just like full blast on, and then they know when to release the power. They because they're experts, and they just go full blast and turn it off with a momentary switch. Okay. Well, same issue. I don't know if it's going to show up really well, and maybe I can clean it a little bit better when it's like a little warm. I don't know. But yeah, lead-free solder is just a little bit more. So yeah, I mean, if I use leaded solder, this will even work even better, right? Because this is lead-free, so leaded solder is going to melt like twice as fast and take half as long. And the reason I only have lead-free is because I actually manufacture these Solderdoodles right here. You're looking at the factory for Solderdoodle. Like, I don't know if you guys realize this, but I build each one myself. I get the parts. I mean, obviously the plastic case I order, all these switch components and circuit boards I order, but I assemble this by hand, each one, right here. Like, and so what I do is I have kind of a lead-free environment. So I try to solder everything kind of RoHS compatible, just because this is kind of an international ordered product. It goes to Japan, Australia. It's kind of funny. A lot of customers are in Australia for some reason. I'm not sure why. But, you know, I try to be RoHS compatible just to kind of, you know, have a mindset of safety and trying to prepare for mass production. So I don't have leaded solder here, but it's all lead free. But um, leaded is going to work even better than and faster and quicker than this. Um, so what I can do now, I can do a speed test, like cutting plastic with the original Solderdoodle, and compare it to the Solderdoodle Plus. So actually, I'll use sleep mode. Go into sleep mode. I could have easily just turned that switch off, but I'm just kind of showcasing the features. So let's see. Here's the blade. So I'm gonna put on the original Solderdoodle, and then we're just kind of do a speed test. This is the same like block that was in the video, Kickstarter video. So here we go. Just gonna cut right through this against the grain, I guess. We're just gonna see how long it takes. And I do remember this taking a while. I haven't cut plastic with the original Solderdoodle in a few months, but I do remember it taking a while, first to heat up and then to cut through. So it's starting to cut through now. Let's see if I can actually turn it around. This might be a better angle. Okay. Okay. So that went all the way through, right there. So I'm gonna let this cool down. Put on the Solderdoodle Plus. I don't know. That was like less than a minute, I guess. In fact, I'm just gonna go over here. And it's pretty cool. Still a little warm. I think a best test is to kind of like cool it down. I'm putting it right in front of this exhaust. This like, yeah, this filtered fan thing. Just get a little breeze over the tip so it cools down. A fume hood. All right, pull it down a little bit more, just so it's a little bit of a fair test. Then we'll cut right along here. Okay. Whoop. Actually, I just turned it on and off again. That's kind of habit. Should have just woke it up from sleep mode. Anyways, should have been like in sleep mode and then triple tap and then it wakes up. Anyways, okay, now I'm gonna go to full power. And it's just touch control. You just slide your finger back and forth to adjust power, right? And then you push on the same touch control with a little bit more pressure, and then it actually turns on the heat. So, oh yeah, let me go in this direction so it's a little bit easier to see. Okay. Let's see. Yeah. There we go. Now it's on. There it goes cutting. That looks a lot faster. I'm not putting a lot of force on it. There you go. That was it. Cut all the way through. All right. I'm just going to do another 12 gauge wire. Now this is actually the thickest wire I could just, test right now. I haven't tested 10 gauge yet, but I have a feeling it can do it. And even if it has a little bit of trouble on 10 gauge, like I said, this is actually at maximum power. It's 5 seconds on, 1 second off, and we can adjust that. Like it's not a limit of the actual Solderdoodle, like inherently. It's just like a control. We had to put in a control parameters in there, right, for the prototype, but we haven't fine-tuned it yet. And I'm almost certain we can even do 10 gauge wire, but this is like the thickest I could find to test out right now. And I honestly didn't think it could even do 12 gauge. I was really surprised what it could do. And this is like, I'm just as surprised as anybody else. Like, why is 10 watts able to do all this? But like I said, just a 60 watt temperature controlled soldering iron requires most of the energy to be used to heat up the thermal mass and stabilize the temperature of the thermal mass. This has no temperature control, so all the heat is just on and off. All the heat goes to the tip, such a low thermal mass that it heats up very quick, cools down very quick, and it almost all the energy goes to the work area. All right. And I just found out about car audio installers, like what their requirements are. Like, I want to say maybe 2 weeks after I launched the Kickstarter project. Because honestly, I didn't know it could compete on that level. I just started soldering these kind of thicker gauges, and like, I was like, wow, I didn't know that was a market I could compete in, and now I know. So I'm just trying to like just show that capability, and I figured, I probably should have done this earlier, but things are just happen so fast. Better late than never. But yeah, I probably should have done a couple live stream like demonstrations like this earlier. It's one of those things. I guess I invented something I didn't even like know its full potential, which is a happy accident. I try to keep the quality as high as I could, and then you run into situations like this. If you put a lot of effort into sourcing good components, good vendors, and sometimes you get a little surprised of how far you can push the final product. So going back to the 12 gauge solder, 12 gauge wire, soldering with the lead-free solder at max power. And like I said, when I did the Kickstarter video, I actually ran it at one level below because I thought that the max power was a little bit too maxed. But I realized that, okay, well, now I need to push this a little bit more powerful so I can do thicker gauge wires. I didn't even, now I know. And the final production run will have all these features in. This is just a prototype. Like once funding is available, we can go into the final production design. This case is actually going to be modified a little bit. I actually let my sister test this out. She has longer fingernails than me. She had a little bit difficult time swiping back and forth, so then I was like, okay, well, I need to, the final design, I need to take that into consideration. So I have to reduce, these edges are a little bit, these ridges are too high a little bit. So I need to design this a little bit lower, maybe even widen this opening a little bit. All these things will be taken care of in the final production. So I'm going to go ahead and solder. So that's full power. It's on right now. All right, it's melting the solder. And so when I timed this for like, I said this can last up to over an hour. That's if you hold this power button down all the way, like that entire time. That's not how the normal use case. That was kind of worst case scenario. Most of the time you hold the power button down no more than a minute. I mean, at that, I mean, I'm probably going to complete this solder in just a few minutes, and then after that, shut it down. And so, so if I do that, like let's say I'm doing, I don't know how many solder like joints car audio installer does, but I would imagine it's a lot. And you just divide that, you know, the 1 hour, 100% duty cycle. You divide that by the duty cycle that you're actually soldering at. You're gonna put a little bit more solder flux. So if you're soldering, each of your solder joints take a few minutes. I don't know how many solder joints do you do an hour? I don't know. How much would a typical car audio installer? I don't know, 5 solder joints. How much does it take to install a car stereo? 10 solder joints. So you say, okay, 10 solder joints, a few minutes. So I don't know, two or 3 times 10. So you're gonna have like 30 minutes of actual like on time. And I don't know if that's a whole day's worth of work, or I don't know, maybe. So that's like, you can use this thing full blast. Like that would be full blast for I don't know, maybe a car audio installer, that's their full day's worth of work. Maybe you won't have to charge this thing for another couple days if you're using this like constantly like that. All right, I think that's fully wicked all the way through. And the duty cycle, 5 seconds on, 1 second off, that's like 83% duty cycle. That's what this power setting is at right now. And we can turn that up with some built-in safety features on the final production run. And maybe I'll try to clean it when it's like super hot. Maybe that'll clean it a little bit better. There we go. Little Q-tip fibers everywhere. So these are hot to the touch. I'm just gonna. These alligator clips are hot to the touch. It's kind of amazing that a 10-watt device can do this, but all the energy is going into the work area. Yeah, that's a little bit cleaner. Oh, that's interesting. Oh, yeah. Maybe over here is a little bit better. It's kind of interesting. There's a little piece of wire right there, a little piece of the bundle that's kind of sticking out, but it's all plated with solder, so it's all silver. It's not. I don't see any copper color. So that's fully wicked all the way through. That's a good solder joint. And let's see. I don't know, what time is it? 11:27. Maybe I'll just keep doing this. Unless someone else wants to see another test, I can do something like that LED test where I'm just like soldering LEDs to a board like that. It's not as up close. I think it's a little difficult. It's a little easier to do this because if I pop an LED through the breadboard and I'm soldering down here, it's a little bit, harder to see it because I don't have a good camera to zoom in this close. I wish I had one of those microscope cameras that some of those soldered YouTube guys do, and it's like right above, and I can live stream it. Let's see. I guess I could do that anyways. I'm just going to put these LEDs to this breadboard, proto board. And I'm going to put a ton of flux, and then I'm going to just kind of real time show you how fast it is. And like I said on my Kickstarter video, I didn't do it at the full power because I was concerned about safety issues. And I thought I was going to have to like reduce the power on the final production, but just looking back on it, I think what I can do is program in some safety features built in to the controller and have it do like 100% maximum power and like shut off if the user like holds the power button down for more than like a few minutes, like automatically go into like cooldown mode or something. That's only on the maximum power. All the other duty cycles, like 3 seconds on, 1 second off, or I think it's 3 seconds on, 2 seconds off. All those other duty cycles, they don't have that issue. There's no risk of like overheating. So on the Kickstarter video, I'm going to put more flux than I did on the Kickstarter video because I actually had to go back and I sped up the speed of the Kickstarter video because it just like Kickstarter videos tend to be very short, and I had to speed it up so I can compress the time of the video so people don't get like bored watching me solder an entire like row of LEDs the entire video. So I'm just gonna, I think it went to sleep. There we go. Wake up with a triple tap, then just slide my finger to go to maximum power, and then I'm gonna go ahead and solder. Let me, is this a good angle? Maybe I'll go like this angle. I'll just move this aside a little bit. Okay. Okay. I need to get closer here. Okay. So I'm at powered on. Actually, yeah, okay. So this is lead-free solder again, and lead-free solder tends to like burn a little bit more easily, which is why you need the flux. So if you don't have flux, it doesn't flow as easily, and it kind of gets that surface crust a little bit easier, and so it's a little bit more tricky. So you need a lot of flux, and you almost get almost like have just one shot at it, because once you start getting that for lead-free solder, once you start getting that surface crust, and it starts to get a little bit black, it doesn't conduct heat, and then you have to like either remove the solder or really like add more flux, see if that helps. Yeah, so like right here, I got just a tiny bit of that surface crust. Actually, cleaning the tip often does help. And then I'm just going to dump a little bit of more flux on that. All right. I think that's good enough. On the Kickstarter video, I actually had a special lens for a camera that can actually do macro photography. So I think this particular webcam is not going to like do it this justice, but anyways, it's all soldered. Here's actually, it's a little bit hard to see, but this last little solder joint is the one that got a little crusty. I mean, it still works, but just the lead-free is a little bit finicky. I probably should have cleaned the tip, like after like the third, maybe I guess either the fourth or the fifth solder joint. I probably should have like cleaned the tip. It was starting to get like a little bit too caked with residue. And so yeah, lead-free solder tends to absorb like crud a little bit easier. Leaded solder is like super easy to work with, and that's why most people use the leaded. It makes a nice shiny, like, and it flows really well. Yeah, I mean, let's see. I think this little joint, some solder moved to the other pad. I'm just going to break that up. And if you're going to do, you know, I want to say if you're going to do like fine soldering, you might want to use a lower power, depending on, like, if I wanted, I wish I had some like other, like maybe some surface mount stuff. Yeah, so like sometimes if it's too hot, these pads will actually rip off. So I would say like if you're doing surface mount stuff, you want to like use a lower power. maybe second to the maximum or third to the maximum. It might take a little bit longer to heat up, but you reduce the chance of actually like getting so hot that you delaminate the pads. Let's see. Here's a tiny copper plate. In the Kickstarter video, well, this isn't in it, but I was testing. I've seen some tests on YouTube where they test the power of a soldering iron by trying to like solder to a copper plate, just kind of like make a giant puddle. And I was able to do that with lead. This is leaded solder on a copper plate. I was able to do that. Let's see. I wonder if I can. Oh yeah. I can. I don't know if you can see it, but maybe I can just like demonstrate doing that on this copper plate. So I'm using a chisel tip that was actually used, I think, to melt this. I don't want to mix my leaded and lead-free. So I'm just gonna basically reheat this, go to maximum power. Yeah, there we go. I'm just gonna reheat this and like turn it, make a puddle. Maybe I can even use like tweezers. I might be able to even move this close with these tweezers. Well, actually, that's a good idea. Because once I get that melted, this whole thing is going to be very, very hot. Let's see if I can get the tweezers. There we go. This is more of like a clamping tweezer. Actually, I wonder if I could just like hold this up like this. Just kind of like turn this whole thing liquid like in midair. It's kind of dangerous. I don't recommend doing it like this, but it's for demonstration purposes. I think this one took a few minutes to actually get to that point where, because it's got to heat up the entire thermal mass of this like copper plate, right? And then it has to start melting the solder around it. So I'm just gonna kind of wiggle this back and forth. So it's still just like surface melting it. I'm trying not to press too hard. If I can make it so everybody can see. Yeah, this side might be. Okay, I can see it's turning into liquid on the surface now. And that's going to increase the conductivity, thermal conductivity, so then more will start to puddle around it. So now more is turning liquid, more is turning liquid. More is turning liquid. And see, I can move this puddle around on this little copper plate. That's pretty amazing. I wasn't expecting this to do this. This is 10 watts. And this is 5 seconds on, 1 second off duty cycle. And we can even like control this on final production to make it even more powerful. I And this is just what I'm able to do right with this prototype. And this prototype is exceeding my expectations. Okay, I don't know if you guys can see that. But it's total liquid right now. And it's kind of dangerous because I'm holding it in midair, but I'm trying to like demonstrate this in this like camera. That's not very good. It's not a very quality camera. I mean, it wasn't like super fast, but you know, it's able to do it. And it's on the thin cover plate, so it's not like a giant, you know, bus bar with, you know, thick giant wires. There's no way the original Solderdoodle would be able to do this. This is the fact that this is twice the power of the original Solderdoodle that's able to make this, you know, this area completely liquid. This is leaded solder. I think when you're doing stuff like this, probably leaded solder is the best way to go. These giant, massive, like blobs. This is the kind of performance you'll expect and you'll get with the Solderdoodle Plus. Let's see if I can. Yeah, I guess you can kind of see it. Like I can do these little swirls. I'm not sure if they pick up on the camera, but it's completely liquid, the whole thing. I'll let it. Let's see if I can let it cool down and let it like change its color as it cools down. There we go. Okay, it's completely solid now. And I tilted it so you can see. I tilt it this way. Let's see if you can see that. It's kind of, see how it kind of like, let's see if I can tilt it this way. It kind of puddled up to one side. Yeah, there we go. So it's like this area is higher than this area because it was liquid and it was tilted like at an angle like this. So it kind of flowed down here. And now it's cool, so it's like this little like mountain right there. There you go. Now you can see that a little better. It's kind of like this hill right here where it flowed downwards, kind of puddled up, but now it's solid, so it's all like a little bump right there. Okay. Now I'll just finish off this wire, just cut this and then do another solder of the 12 gauge wire. That off. Do the old car mechanic trick. You just kind of smash these together, and then give it a little twist. Okay, I'm gonna do this one more 12 gauge wire soldering demo. Put a bunch of flux. And switch the tip for the lead-free tip I was using for lead-free solder. And like I said, this is all lead-free solder, which is higher temperature, requires higher temperature to melt. So leaded solder will melt a lot faster, easier than this. So if it works for lead-free, it will work even better for leaded. So it's on maximum power. Let's see if I think I have enough solder here. All right, activate by pressing the touch control down. It's already melting on the tip. So I'm going to go ahead and just move across to get this kind of surface solder first. And that starts to increase the thermal conductivity throughout the wire bundle. And then that heats up the wire bundle even more. And then when the entire wire bundle gets up to temperature, then it starts to wick into the wire bundle. And if this is 10 watts, like I said, this is something you'd expect out of a 60-watt soldering iron with temperature control. And this is just 10 watts, and its duty cycle is 5 seconds on, 1 second off. So on a final production run, we can increase that even more, and then built in some safety features. Add a little bit more flux. And this is the only flux I have. I think there's some better like heavy duty flux for these kinds of things. The flux I have is more for like small electronics. So I think there's flux where it's like in a jar and you just kind of stick the whole, like either like just kind of like glob it on with like a giant brush. I think that might be better for this type of application. And you want to get the solder all around. You don't want any exposed copper, and you'll know because it'll like be an orangish color. You want everything to be silver. And the only way to do that is to have a soldering iron that is powerful enough to heat up the entire wire bundle so it can wick into each and every of the bundle fibers. And this is the chisel tip. In my previous Solderdoodle Kickstarter, I think a lot of people didn't like, well, not didn't like, but prefer the chisel tip. I actually, I prefer the conical tip, to be honest. But I think a lot of people prefer the chisel tip more. So that's why I'm doing all my demonstrations with now. And I think chisel tip is actually a little bit better for thicker gauge wire. One of the wire fibers kind of came loose a little bit. I just kind of tucked it back in. All right. Just gonna like clean it up a little. So I'm really happy with the Solderdoodle Plus like prototype. I I foresee me not being, you know, having to have a plug-in soldering iron. I mean, so here's a Metcal soldering iron tip. This is what I've been using for the production of Solderdoodle um, for the switch area right here. Inside there's an actual metal contact that I wire lead-free solder with this Metcal tip. But you know, the ideal like situation is where you can have one Solderdoodle make another Solderdoodle, and that is kind of mind-blowing, right? Because then you kind of like uh, you're kind of like obviously the first one you have to build from other using other tools, but you can imagine the situation is where the technology is to a point where this is powerful. The Solderdoodle Plus is powerful enough to like create another Solderdoodle. Now, but however, like with this new circuit board that I designed, I actually try to make it more manufacturable. So now we have battery clips. So these battery clips, you can pop in new cells. The idea is like this should be able, because there's a charge controller right here, charge controllers on each cell. So there's 2 charge controllers to maintain the battery voltages exactly within the limits of its charge range. These cells should last a lot longer than any like spot welded pack that you find in other battery packs. The reason I did this is if you solder the 2 battery packs in series, you get a pack that the individual voltages of each cell cannot be determined in real time. So you have to shut off the charge current and go into cell balancing mode, which then starts to balance out the voltage of each cell. But you can't do that at the same time. So but with a charge controller on each cell, you can do that in real time. And so eventually, maybe not immediately, but if you have a welded pack and they're like 2 batteries that are welded together, so like this, most of the time you'll have positive to positive welded together, right? And negative to negative welded together in a pack. And so each cell, you're not sure what the voltage is because you're measuring the voltage of the entire pack. But with cell balancing, you have a way to not when they're you have a way to actually not in series, but you get the series, like series packs are then combined in parallel. So you'll have each of these parallel packs, the voltages are controlled. But actually, when you're in series, it's almost impossible to tell the difference. Well, actually, it's opposite like this. I'm sorry. This is parallel. Positive, positive, negative, negative is parallel. This is series. Negative to positive, and then these are the output. So you'll measure like positive and negative, and then one side is welded and the other side is the actual output. So when you do that, when you're in series like this, you can't tell the difference between the voltage in each cell. When you're in a parallel mode, like positive to positive, negative to negative, you can actually shut off. You have a circuit in between that actually can isolate each cell. But when you're like this, you can't, because your output is these negative and positive, and this portion is welded together. So you have basically a single ground that you have to base your voltage off of. And so if I undo this and I try to measure, let's say, here's the weld, I break this weld, and then so here's negative, or here's negative, I break this weld, and I try to measure, I don't know, the reference off of this negative. I create like a short, like because these two grounds are now like tied, and then this battery gets shorted. So anyways, when you do when you do these packs in series, and you try to cell balance each series pack in parallel, one of these series modules may eventually one cell will get overcharged, and you don't know to what extent that is. And engineers design this in their battery packs. So an engineer, when they're doing these like series and parallel packs, even for a Tesla car, they will say, well, we understand that some cells are going to go bad because some cells during the balancing process are going to get overcharged, even under discharge and overcharged. So we're going to anticipate that, and our specifications are going to account for that. And they will have circuitry in their balancing and charge control boards that will detect a bad cell. Bad cell is just basically they'll detect a bad cell, either not taking a charge or some defect about the pack that's not charging, and they'll just remove this whole pack from the circuit. And that's how they control, in today's world, that's how they control battery packs, especially large ones in like a car. And they're water cooled because of, they're like have to be maintained, like really cooled very carefully. So what I did is I put each cell on an individual charge controller to avoid all those issues. So no more guessing and accounting for cell failure. If a cell will, the only way it would actually go bad in this situation is if you left like never charge this for like a year or two, and then it starts to get self-discharge over a long period of time. And even if it does, like the life cycles of a cell, they'll say, oh, good for 500 charge cycles. That means full discharge and recharge. Well, according to the manufacturer's spec, a life cycle specification just means to a point at which the capacity starts to drop off. It doesn't mean that the cell dies after 500 cycles. And if a cell does die after 500 cycles, that means the engineer didn't do a good job at designing or supplying the quality materials, because lithium-ion batteries never should like just die. They should, over time, just lose capacity. And so the spec is like over 10% loss in capacity. We'll call that a life cycle, end of life. Because a company can't ensure that the battery will hold its capacity forever. They have to cut off at some limit. So you'll see specs of 300, 500 life cycles. But after that, it should still hold a charge. So this has a 2,000 milliamp hour capacity. So after 300 to 500 cycles, it's going to lose 10%. So now it can only hold 1,800 milliamp hour capacity. Well, according to Panasonic, these are Panasonic NCR 18500A type batteries. According to Panasonic, that's end of life. But to us, that's like, wow, end of life, but it still has 1,800 milliamp hours left of capacity. That sounds pretty good to me. Yeah, but it should be amazing, because that's lithium-ion technology is amazing. And that's where we are right now. We're at a point where the lithium-ion battery technology is you'll find a lot of consumer electronics out there that are kind of putting a bad name to lithium-ion technology, with phones and other devices, tablets that just like die after like a year of use. And that has nothing to do with the technology. It has to do with the engineered design and sourcing of components. And in a world where CEOs are cutting costs, cutting corners every day, they're going to say, hey, why are you spending $2? You know, each of these chips, each of these charge controller chips are $2.50. Okay. If I'm a CEO, I want to reduce the cost by 10%. You know what I'm going to do? I'm going to take out one of those charge controllers because that's a expensive part. Because you know I'm going to make 1 million of these times $2.50. Oh man, that's $2 million in savings, right? But this is going to be a lower quality product. It's not going to last as long, and now the whole world is going to be flooded with products that don't last, and it's going to give lithium-ion technology a bad name. I mean, that's the world we live in. It's kind of sad, but we have the technology now to power everything by batteries now, and we don't have to be attached to the wall socket anymore. We're there. It's the year 2018. We're going into the year 2019, and we're still plugged into the wall for some reason. Now we have table saws that are powered by lithium-ion battery packs. All my drills and saws are all battery powered. They all last all day, and for some reason they're not being this kind of long-lasting, lifelong-lasting technology is not being in the main consumer electronics market. It's kind of only into these niche, either cars or high-end power tool types of equipment. I mean, if you're paying $1,000 for a phone these days, you expect this type of quality. And if you're not getting it, has nothing to do with the technology itself. It's decisions by the heads of these corporations to reduce cost. Save $2 per unit. Like that's the main thing. But either way, I did still have these clips because it's easier to install. Let's say I'm at a factory, so I want to install this. Well, this is all I have to do. I just pop clips in there. Now, to be honest, I wish I knew about these clips when I designed the first Solderdoodle, because the first Solderdoodle is actually spot welded tabs and crimp connectors. I'll show you the difference. So I'll just show you one more time. This is the original Solderdoodle Plus prototype. This giant spaghetti monster, right? Here's the original Solderdoodle. Imagine me going to Kickstarter with this, right? You guys probably wouldn't want to fund this, right? So, but here's the original batteries that I was testing on it. So what I was doing is spot welding and tabbing and crimping each of these cells by hand. I still do that to this day. So this goes into here. And it turned out that was, even when I tried to outsource this manufacturing process, it was very expensive, and a lot of vendors didn't even want to like do this. And they already had pre-existing packs like this, but they didn't use the high quality Panasonic batteries, and the vendors would push back against me saying, why don't you use Samsung? They're cheaper. Why don't you use, cheapo Alibaba special battery or whatever, right? Like, and I was like, no, I want this Panasonic. And they said, oh, we can't do that. Because you know, they have to supply it, or they can, but they have to order it because they don't have these in stock, and they have to get, because they have the cheaper ones in stock. And then they said, oh, that's going to be like, I don't know, $16 per cell. I was like, okay. But, you know, just learning about how to design a little bit better, these clips, you just pop it in. And I had to design, you know, make sure that when I was doing my 3D CAD design, make sure that all these dimensions, you know, fit perfectly. So when these clips were installed into the PCB, that it was just the right distance so that it would have the right amount of springiness to hold these clips, hold the battery with these clips like this. And you can place these clips in any distance you want for any size battery, really. And so I placed it for the 18500 batteries. The reason that I use the 18500 and not the 18650s, and you can see the size difference right there, is because this, if I use the 18650s, it would make the Solderdoodle Plus very, very long. And I did try that at first. I have a prototype. So here's the original prototype for Solderdoodle Plus. It was going to have these batteries inside, you know, right in there, and it was going to be like this massive thing like this. And you know, I can show it side by side, you know, the size difference. And then I have to have two of those. And so, yeah, in order to get it well balanced and in the hand and feel kind of ergonomic, I went with the 18500s. And there we go, it's in sleep mode. So that's cool. It was still in sleep mode this whole time. I guess I could just show the here's the control. So this is the microcontroller right here, and there's actually a way, if I have it here. So all these instructions on how to build the Solderdoodle Plus is on Instructables.com. There's a link in the Kickstarter page for it. But if you had a programmer using Arduino, or well, actually, I'm using a Teensy, but you can use an Arduino as well. So you can, and using the Arduino IDE, you can actually plug into these 6 pins that are right here. So there's a 6-pin programming interface. So if you unplug from the main board, the main so the Solderdoodle, inside the Solderdoodle Plus looks like this, right? So let's see, let me move this out of the way. Okay, so you unplug from the battery pack, and you can actually go into the programming pins, and all the code is available on Instructables.com. You get a little like, I have the schematic for even this, the pinout for this programmer. And you just place it. Let's see, this way, yeah. Have little pogo pins. then you just kind of press it in a little bit. Okay. And then you go ahead and program it. And then you can actually modify it if you're good at coding. And who knows what you can come up with on like modifying it to power all sorts of stuff. I mean, this literally is a 5-volt, 2-amp power supply if you wanted to use it for other things. I was actually considering doing a foam cutting attachment to this, but the only problem with that is because it's kind of like a barrel kind of jack attachment, it's really easy for this to spin and rotate. Well, not super easy, but it can rotate while cutting. So it would have to have some sort of clocking mechanism for a foam cutting device to prevent any rotation of the cutting tip. You know, actually, maybe I could just show you that prototype. I mean, it's not, I don't have it, but what the heck, right? Like, just to show you what kind of stuff I've been playing around with. So here's the prototype. It's a little silly, but this is probably the longest I can get out of the. I think this is nichrome wire. I think it's the same wire used in vapes, and this is actually an attachment from the company that provides me these heating elements, and I attached it to one of these, screw terminal to this is actually RCA jack, and then I could just like plug it into here. That's a little ridiculous, but I mean, as an inventor, you gotta like try lots of things, see what sticks, right? So let me get a piece of foam. All right, here's a piece of foam. Here's that prototype, foam cutting tool. Wake it up. But the only problem is I actually have, this is set to duty cycle, so it turns on and off, right? That's how it controls the power. Oh, see, so kind of already started to smoke. So the problem is while you're cutting, it's constantly turning on and off. So I'll show you. So it's going to cut, right? It's cutting, and then it's going to kind of stop. See, it just stopped, and it's going to start cutting again, and then it stopped. And it's going to cut some more. Like, go at another angle, and it stopped. Cut again. So, and then this has, like I said before, it can rotate on you really easily. So that's one thing I was concerned about. I haven't figured it out. So with this particular device, I would probably have to redesign the whole heating element to do that. But if you wanted to, as someone who wanted to modify this, for example, and wanted to just hack different attachments, you could do it. And I could have this like 100% duty cycle, 100% on, with no limitation. But that, I think, combining that with the other attachments is a little dangerous. the other heating elements, that if you leave it at 100%, it will get too hot and overheat. This won't if I leave it on, but full blast, it won't destroy itself, but it won't overheat. But it's having a setting just for foam cutting might be a little bit too dangerous for the other attachments. So maybe that's a project for the future of Solderdoodle. I don't know, just trying to find as much applications as I can. But this is the kind of stuff you can do when you do taking the time to make a high quality power supply. That's what this basically is. It's a 5 volt 2 amp power supply, and then combining it with a microcontroller. This actually this particular power supply can output up to the wires that the cables that are in there are rated up to 5 amps, and this is actually a tiny little 5 amp fuse. So you can run it up to 5 amps, and it's not going to blow the fuse. You probably don't want to go at 5 amps, but maybe like 3, 4 at the max. So you can get 15 to 20 watts out of this thing, no problem, just with this circuit board itself. And it's got, here's the connector. We have it's 5 to 8 volt, 5 to 8.4 volt out. Then we have ground, and then we have 2 5 volt outputs. The 5 to 8.4 volt out here is the actual series battery pack voltage, and the other ones are regulated 5 volt regulated voltages, which are specifically designed to power the microcontroller and LED lights. These are little dot star. They're AP102 RGB LEDs, 7 of them, and the so the 5 volts coming out of this cable here, connector there, is powering the LED lights and microcontroller. The 8.5 to 8.4 out here is powering the actual 10 watt regulator, which is up here on this side of the board, and that's 5 volts 2 amps exactly. It's really stable 2 amps also. It's just like dead on 2 amps. And so I'm hoping not just this Solderdoodle project, but future projects that I do will use this kind of isolated ground technology. And that way you can just, my idea is somehow make packs that are able to kind of, like Legos, just kind of snap together and have them all like individually isolated, grounded. And then you could just like remove an entire like little pack and add a pack without having to solder everything together and reconfiguring the entire assembly of your pack. I have a feeling this is kind of, it might be the way to do it. I'm not sure why other companies aren't doing this. I have a feeling it's just cost, because if you're like have a giant pack of 7,000 cells and you have a charge controller on each cell, well, that's like a lot of money. So I think there's a lot of cost issues with that, but I'd rather have a battery pack that just has like 5 to 10 years life than like have like a cheaper pack that you have to constantly like throw away or like replace, because by the time you purchase these like $10, $5 packs that are like welded together, after, I don't know, you throw away 5 of them, that's $50 right there. So might as well pay like, I don't know, $30, $40 for a high quality pack that lasts like twice, 4 times as long. So yeah, I mean, just trying to improve the market. I want to keep everything open source. I'd rather live in a world where battery packs just kind of last a lifetime. And for whatever reason, if they do go bad, it's just real easy to replace. You can just snap it in. And it's going to be the year 2019, and I think we need, it's about time we get products that just last, last longer than what's out there right now. It has nothing to do with, we don't have to wait for new technology to come out. It will, we're there, we have it. And I mean, if I could build something like this in my apartment, I think these big corporations could do it a lot more easily than I can. Let me see if I could have a little bit more wire that I can solder. Let's see. Yeah, I think I used up all my wire. Unless anyone else has another. Oh, wait a second. Oh, I think this is another little piece of 12 gauge. Let me just solder. I'll solder one more piece. All right, that's the piece I just soldered. Okay, just gonna maybe 2 more of this. Probably just 1 more. Oop. All right, 1 more piece. I don't know if the people watching are the same people, but if you're new, I'm just gonna say this is 12 gauge wire. And this is a trick I learned from car audio installers that I was talking to right after I launched this, and realized tricks and that Solderdoodle Plus could be very useful to them. So car audio installers, they just kind of mash them together like this, and then they just do a little twist. And that's like a kind of quick and dirty way to like get these to join rather than twisting them in like a knot. Okay, so I'm going to use the chisel tip, and this is lead-free solder. So leaded solder is much easier to use, and so basically, if this works with lead-free solder, it will work even better with leaded solder. So I'm going to add some flux. You really want to use flux when, especially using lead-free. And doing these like really thick wires, I have seen the car audio installers, they have like kind of a thicker paste. This is more for like smaller electronics, but when you're doing thick wire like this, you'll have like a jar of like flux, and you just get a brush and you're like painting it on. Okay, I'm gonna get. I don't think this is enough solder, so I'm gonna cut one more piece. And I'm just gonna, I'll do one more test actually with showing the difference between the original and the Solderdoodle Plus. Since this is the last wire, why not? So here's the original Solderdoodle, and it was fully charged when I did this demonstration earlier. Turn it on. So this is the original Solderdoodle, and I'm just going to show you, like, the original Solderdoodle has a lot of trouble doing thick wire like this. And the original Solderdoodle is rated for 24 to 26 gauge wire. You know, thin wire, like doing Arduino type projects, proto board type stuff, soldering LEDs. So it's starting to melt right now. And so now I'm trying to get the solder to flow onto the surface, but I can tell I'm just kind of getting a surface melting. So what that means is the heat isn't really strong enough to melt the solder and also heat up the copper wires beneath it. And so the original Solderdoodle doesn't have any duty cycle control. It's completely on off, but it's the voltage of the battery itself which creates the power output. So fully charged single cell is going to be 4.2 volts. And I think the current coming out of here is like a little over an amp, maybe 1.4 amps or something. So you're getting, you know, like 5 watts around that. And yeah, it's not even able to melt. Yeah, it's just completely like bouncing off the surface. I can get a little bit to stick, but it's just kind of like bouncing off the surface of this this wire. And that was the original issue with this original Solderdoodle, is it had a single cell and it could do a lot, but it did have limitations. I would say that the original Solderdoodle is not a complete replacement of a wall socket temperature controlled soldering iron, but it was one of those portable devices that you can take with you for small jobs that you didn't want to bring your entire, like, you know, soldering iron station with you. So I'm gonna swap to the Solderdoodle Plus. I'm gonna use the same tip. And the tip's like already cooled down. Clean that. I'm gonna put a little bit more flux. Actually, maybe I can show, get a little closer. Yeah, this camera's not that great, but anyways, it's complete. Like, you can see the color is not silver; it's completely like copper color, which means it didn't flow at all really into the solder didn't flow at all really into the wire. So I'm gonna add more flux. And again, this is 12 gauge wire, and I have a feeling it can even do 10 gauge wire. I just haven't been able to test it. And like I said before, this is just a prototype. So the control this is duty cycle control. So it's 5 volts output, 2 amps constant, like really constant. It is like dead on 2 amps each time I push the power button and activate it. And it's duty cycle controlled. So at max power, it's 5 seconds on, 1 second off. Okay, so I'm gonna activate it by, so I adjust the power by sliding my finger, and then by pressing harder on the touch control, I activate the heat. And